It's a great pleasure to be here with you. Thank you very much for the invitation to visit Colombia, which I've not been to this part of the world previously, so it's been a very nice experience. Okay. So I will try in the next 45 minutes or so to give you a very rapid run through some of the recent results which we've had, mainly from the Atlas experiment actually, although I do also have some results, some of the really wonderful high-profile results which have come from CMS as well. And I'm really going to be focusing almost entirely on the results, the latest results from Run 2 of the LHC, with a few others on standard model measurements later on, but you'll see what I mean by that later. So really just to say, when I was preparing this talk, I was looking at some of the sort of local cultural artifacts, and I saw this picture of one of these artifacts from, I guess it's in the Gold Museum in Bogota, and I remember seeing this as a child and being incredibly impressed by this amazing miniature sculpture from, I guess from the pre-Columbian society. And so, of course, here I am here we are in the land of El Dorado, and what I hope to convince you over the next 45 minutes is that really we are now in the El Dorado of scientific results from the LHC. We're really having an amazing flood of of results which are really probably giving us the promise or fulfilling the promise that we've been really anticipating for many years now for the LHC experimental program. And this really bears a lot also on what John was saying earlier on in terms of the inputs to the theoretical understanding of the standard model and beyond. So I'm going to be talking mostly about the results from Atlas in relation to the data that was taken actually in the 2015 and 2016 data set. The analysis of the 2017 data set is very much underway at the moment. As many of you may know, the 2017 running just finished a few weeks ago. So the first results with the 2017 data will be coming out sometime in the spring next year. So I'll be mostly talking about the 2015 and 2016 data, and therefore I will also say a bit about the data taking and performance in 2016, which fed into these results, and also a little about 2017. And then I'll say a few words about the longer term future as well. So as I'm sure you all know, the Atlas experiment is a really incredibly large and complicated piece of equipment. It took the combined efforts of many thousands of physicists and engineers over several decades to design this and put this together. And of course the complexity of such a device means that really this is an endeavour which can only be undertaken by close collaboration with experts from across the world. So of course we have very major contributions from many places, including from Latin America and from Colombia. And of course for the future, as I will come on to at the end, we are very keen to improve and upgrade this experiment for running at the higher luminosities that we accept from the LHC in the mid-2020s onwards. And for that also, I would say there are many opportunities available for new people and new groups to get involved to really make major contributions to the future scientific program of the experiment. So in 2016, as many of you may know, the LHC was performing particularly well. We had record instantaneous luminosity for proton-proton collisions. We accumulated something like 40 inverse femtobarns of data in PP collisions. And in addition, we had heavy ion collisions, proton-lead data taken at 5 and 8 TeV. In Atlas in 2016, we recorded 35.6 inverse femtobarns. We had very good availability of the experiment, and most of the results I'm going to be showing you today use the combined 2015 and 2016 data sets. So this comes to 36.1 inverse femtobarns. You'll actually see some CMS results, which I will show also. Those have 35.9 inverse femtobarns. The numbers are very similar. In fact, the luminosity calibration is somewhat different in CMS and Atlas. And in fact, those results were in fact largely just using the 2016 data set. Now, the key challenge which has faced all the experiments in 2016 was the pile-up, as it's called, of minimum bias or soft interactions, which lead to something like, you can actually see in this diagram here, in 2016 of order 25 interactions per bunch crossing in the LHC. In fact, it went up to more like 45 or 50 at times. And in fact, the experiments were designed with a pile-up interaction rate of something like 25 interactions per bunch crossing as their design goal. So this was really testing the design of the experiment, but even in the very earliest parts of the runs, when the luminosities are even higher, as I said, these interaction rates could be even higher, and that's a key challenge for the experiments to cope with this. You can actually see from this is an event display from run 1. You can see here 25 minimum bias interactions lined up along the LHC beamline, helpfully coloured in. Of course, the data is not coloured in, so this is the result of very sophisticated reconstruction algorithms from Atlas. But you can see each of these dots is an interaction, and then you have to pick out the hard scattering high PT events, such as here we have a Z to mu event, against that very complicated background. So I'll say a little bit about that as well in a second. The LHC has continued to set records in 2017. So we've recorded something like 47 inverse femtobarns with 50 inverse femtobarns delivered, and the pile-up interaction rate has increased still further, and that's what you can see over here, and I'll come back to this in a second. So very briefly, in 2016, the trigger that we have for selecting interesting events in the experiment performed very well. We have something like 2,000 active menu items, both for collecting physics events and also for monitoring and understanding the performance of the experiment. And one potential challenge there is that as the pile-up rate increases, then this can greatly increase the trigger rates for some triggers beyond just a linear increase. You can actually see this here for missing transverse energy triggers as a function of the number of interactions per bunch crossing, so the pile-up rate. And so if you just apply a somewhat naive trigger algorithm, you can see that the rate, called the cross-section here, the trigger cross-section, increases far more than linearly with the interaction rate. Whereas if you apply certain other mitigation strategies, you can then keep this rate to a much more manageable level. So a lot of work has gone into ensuring that these trigger rates are under control, even at very high pile-up. Offline reconstruction, then, so reconstructing the data which has come off the experiment, again, the challenge here has been maintaining the performance in the presence of very high pile-up. And again, largely in Atlas, this has been achieved very, very successfully, particularly because we've looked very closely at the data and ensured that our algorithms are very robust. And you can see some examples here. I'll just highlight one of them, actually, on this slide. So this is looking at reconstructing the Z mass in Z to EE events, which is, of course, a key standard candle, if you like, or calibration channel for understanding the performance of electron reconstruction in a collider. And you can see here is a function of mu, which is the average pile-up rate, or the average rate of soft interactions. Broad range here, you can see that there is very good stability to the sub-per-mil level in terms of effectively the position of the mass peak in Z to EE events. It's extremely stable across this broad range of mu. So that's a good indication that the reconstruction is robust. And we see similar behavior in all the other physics object reconstructions that we use in Atlas. B-tag jets, for instance, or jets, missing transverse energy, muons, etc., etc., etc. Okay. So just to say a few words about 2017, as I said, the instantaneous luminosity was even higher in 2017. So we got up to 2.1 times 10 to the 34 in the appropriate units for instantaneous luminosity. Generally speaking, in Atlas we were leveling the luminosity, which means that the machine are effectively tuning the interaction rate to something like 1.55 times 10 to the 34, or a pilot rate of something like 60, which then minimizes the dead time in the trigger. And so this enables us to function very effectively. In fact, we lose very little integrated luminosity as a result of this, and CMS actually were doing something similar, as I understand it. Again, the detector performed extremely well, and the online and offline reconstruction performance was maintained even at the very highest pile-up. So these plots here are very similar to those that you saw on the previous slide, but now these are in 2017 data, and you can see these new values or pile-up values go to even higher values, up to 55 or even higher, 60. So again, the performance is robust. So I'll move on now to a few of the results that we've obtained. I'm going to start with searches for new physics, and I will come on to supersymmetry later, but I'm going to start with the non-supersymmetric exotic states. So really here, as experimentalists, our job, I would say, is to really take a sort of a somewhat agnostic view from the point of view of theoretical motivations. We are driven by signatures that for possible new states that we can look for, and then we can interpret the results of those searches in the context of particular models. I don't have a chance to go through all of these many results that we have. I've highlighted in just a few red boxes here some of the results which I will cover. And I'm going to start with searches with digets. So this is perhaps one of the simplest and most straightforward searches which you can undertake at a Hadron Collider. Here you're basically looking for, the simplest approach is to look for resonances in dijet pairs in PP collisions. And of course that's a QCD process, so there's a very large QCD dijet background. But we are looking for peaks from resonances at high mass in the dijet invariant mass spectrum. And you can see an example of the distribution here. These overlaying points here are model predictions for particular resonances. But as you can see, in fact, the data, which is in black points, agrees extremely well with a smooth distribution, which we've parameterized from QCD simulations. And so as a result, there is no evidence for a significant excess. So we can set very stringent limits on a whole range of possible models which give rise to dijets in the final state, excited quarks, additional gauge bosons, quantum black holes, contact interactions. That's using a slightly different approach, which I don't have time to go into right now. But you can see the mass limits on these states that we're setting now are in the multiple TeV range. So these are very stringent constraints which we're obtaining. Then moving on, we can then now look for resonances with leptons in the final state, and the two sort of canonical examples here are looking for dilepton pairs or for looking for a lepton plus missing transverse energy. And of course this is, in the standard model, is equivalent to a Z or to a W. So we're looking here for Z primes or W primes, additional Zs or Ws. Again, we can compare the data invariant mass distribution for, in this case, for instance, electron positron pairs, or here for a muon and missing ET transverse mass distribution. And again, we can compare with the theoretical standard model predictions, which are the histograms, and again, you can see exceptionally good agreement between the data points and the predictions. So again, there is not no evidence here for additional states, and so we can set exclusion limits on the masses of these states, in particular theoretical models. So in one particular benchmark which we often use, which is the so-called sequential standard model SSM, we are setting the mass limits here for a Z prime, a Z prime of something like 4.5 TeV, and for a W prime of 5.1 TeV. So again, these mass limits are going well into the multiple TeV region. Increasing in complexity, now we can look for resonances not of the states that we see directly in our experiment, but instead resonances of resonances. So in other words, resonances where the resonance has decayed to a diboson, standard model diboson pair, so a Z or a W, or possibly a Higgs actually. And so we can, these are much broader range of searches, because if you think about it, the Zs, Ws and Higgses can themselves decay into a broad range of final states, characterized either by hadronic states, so jets, or with leptons, or possibly with BTAG jets. So there are many searches undertaken in ATLAS which are searching for these resonances with these various final states. Broken up by these the decay products of the standard model bosons. And one thing which we can do is when we have very heavy resonances, this will then cause the standard model bosons which are producing the decay to be boosted to very high transverse momentum. And in such cases, we can use what are called jet substructure techniques, where we actually look for merged jets coming from, for instance, a very high PT W or Z, where the W or Z is traveling at such high PT that the two jets from the decay products merge into a single jet. And we can identify that with these very modern jet substructure techniques, which is collectively referred to as boson tagging. And that can help gain us sensitivity at the very highest mass. Again, we see no significant excess over standard model expectations, and we set limits in a broad range of scenarios. So also extending a bit further the searches for resonances, we can think of other final states. So one area which I think attracted a huge amount of attention, both in the community, experimentalists and theorists, and also in the wider world, back in at the end of 2015, was where we were looking for the results of our searches for diphoton resonances. And as I guess many of you will know, there was some hint that there may be something happening at a mass of around 750 GeV with the 2015 data. These have now been repeated in 2016. And now we have the results with the full 2015 and 2016 data set. And in fact, as you can see here, there's basically very little happening at 750 GeV in the diphoton invariant mass distribution. So there's, in fact, unfortunately, it would be very nice to have some evidence for new physics in this channel, but unfortunately there's very good agreement between the predictions and the observations. So again, the mass limits that you can see here, or the cross-section limits as a function of mass, you can see there's basically no significant excess at 750 GeV or anywhere else. In fact, the little wiggle here that you can see is just a remnant of what was happening in the 2015 data set, which is, of course, included into the combined 2015 and 2016 analysis. We also have searches for di-tau final states. Those are sensitive to additional higher mass, for instance, Higgs bosons, possibly predicted by supersymmetric models. And again, these see no evidence for an excess, but set very stringent limits on the MA tangent beta parameter space that characterizes the Higgs sector of the SUSY models. Dark matter searches, we can search for dark matter in visible final states by looking for the production of dark matter states alongside a visible standard model state. So you end up in the detector with a standard model state such as a jet or a photon, for instance, plus missing transverse energy created by the recoiling dark matter particles. These are complementary to the direct dark matter searches. For instance, we have good sensitivity in many models to quite low mass states. It's a very rich phenomenology for these searches because what the signatures in ATLAS or CMS depend on the mass of the dark matter particles, the mass of the heavy mediator state, which couples the protons to the dark matter particles, and also the type of couplings. And of course, one thing also to remember is that for us to be sensitive, then this mediator must couple to the quarks and gluons and the proton by definition, because they're in the initial state. And this means then that the searches for decays to dijets, which I discussed a few slides ago, are also very powerful, because there you have the quarks or gluons in the initial state coupling to the mediator, but then instead of that then coupling to dark matter particles, that could then couple back to quarks and gluons and give you a dijet final state. So we have one example here is a search for jets plus missing transverse energy. So you see here the missing transverse energy spectrum, and again there's good agreement here between the data and the standard model predictions. And we can compare the sensitivity of these searches here in a particular model scenario, so with a particular mediator and a particular set of couplings, also with the sensitivity which we obtained from the dijet searches. You can see these are also very, very powerful, excluding broad ranges of this parameter space. So in terms of searches for supersymmetry, this is the bedrock of the ATLAS and CMS experimental program for many, many years. And the searches for the light quarks and gluinos with jets and missing transverse energy signatures, those are now extending to mass limits on these particles, which are above 2 TeV for the first time. So you can see in this summary diagram here, which I wouldn't expect you to read the various lines here. Each one of these corresponds to a separate channel in a particular analysis. So there's a very broad range of analyses being undertaken. But the first and most sensitive searches are now setting limits which are exceeding 2 TeV. There's no significant excesses over standard model expectations, but with this extended data set, the sensitivity is extending well beyond the previous results from 2015. So now there's increasingly in the experiments there's a big focus on natural SUSY models where we have relatively light third generation squarks and Higgs-xenos to cancel the divergences in the Higgs mass that John was mentioning earlier on. So we have direct searches for stop pair production, so these are the SUSY partners of the top quarks, or for spot-em pair production, or for production of direct production of charginos and neutralinos. And again, the reach of these searches is extending now up to something like a TeV for lighter SUSY particles, which occur at the end of the SUSY decay chains. So far we don't see any significant excesses, so we set very stringent limits on these masses. And in addition, there's a renewed focus on more challenging signatures, which could allow low mass SUSY states to escape detection with all the analyses which we've undertaken so far. So for instance, searches for R-parity violating models, which do not typically have a missing transverse energy signature in the manner of these other models, or for instance, long-lived signatures of mass degenerate SUSY states, where for instance, we could have heavy charged particles traveling out through the detector, which we can observe, or for instance, where there are decays inside the detector, where we can, perhaps with a displaced vertex away from the initial interaction point in the LHC. So again, this is another focus which I think will get an increasing amount of attention over the next few years as we run through to the results with the full run-2 data set in a few years' time. Okay, so I'll move on to studies of the Higgs boson. This, as John mentioned, we're now 5 years in after the initial announcement of the discovery, and actually, just I thought in the spirit of that discovery, this is the one slide I have on which I have a Comic Sans font, which is the official CERN font for Higgs discovery announcements. So with the latest data set from ATLAS and CMS, we're now really able to make, in many cases, high precision measurements of the properties of the standard model. We have a larger data set than we had in run 1, and we have a higher center of mass energy, so we can make more precise measurements, and we can also make additional measurements which were not feasible previously. So the workhorse of these measurements are the channels with Higgs decays to 4 leptons via a Z and a Z star, or decays to 2 photons. And with the data, this current combined data set, we have now made measurements of the, for instance, the cross-section for production of Higgs bosons at 13 TeV, which are in exceptionally good agreement with the most recent theoretical predictions, which you can see this blue band here. So in terms of the production cross-section, this seems to be in good agreement with the standard model expectations. Another way to put that is that the global signal strength of our observations is compatible with standard model expectations. The global signal strength is 1 if the measurements are exactly equivalent to the standard model expectation. And you can see here that for this combined cross-section measurement that we have a signal strength of 1.09 plus or minus 0.12, so it's an extremely good agreement with the standard model. We can then also, with this larger data set, we can start to do more complex measurements. One example is we can start to perform differential measurements. So for instance, differential measurements of the cross-section for production of the Higgs boson as a function of the kinematics of the Higgs boson itself or of additional jets in the event. So you can see an example here for Higgs to gamma-gamma events. You can see the black points. This is the PT, the transverse momentum of the Higgs. And you can see this again compared with the latest theoretical predictions. We can also interpret the cross-section measurements in various different categories, which are sensitive to different mechanisms of production. So for instance, gluon-gluon fusion and vector boson fusion. We can interpret the cross-section measurements in this plane where we plot the cross-section for each production mode on the 2 axes. The standard model is, it's not very easy to see it on this figure actually, it's this blue, very small blue ellipse just there. And our measurements here, they're perhaps a little bit high at the moment, but they're reasonably consistent with the expectation. And there are also a very broad range of additional measurements which are being carried out at the moment. And if you're interested, please take a look at some of the references which I've included here currently to Atlas COMHEP's preliminary results, which will be followed up very soon with papers. Measurements of the Higgs boson mass have restarted now in run 2. Again, these are carried out with the 4-lepton and 2-photon channels. The measurements which we obtain in Atlas are consistent between both between the 4-lepton and 2-photon channels, and also internally in the 4-lepton channel between the different lepton flavors that go into that. So, for instance, 4 electrons, 4 muons, 2 electrons, and 2 muons, etc. So there's good internal consistency. The 4-lepton and 2-photon measurements are consistent within 0.4 sigma, and the combined measurement is consistent with run 1. So in Atlas we have 124.98 GeV plus or minus about 280 MeV from run 2. So the precision currently in Atlas is still a little bit less. It's a little bit less precise than the combined LHC run 1 measurement. But this will be improving as we get more data. So there's also a CMS measurement, which John mentioned, which is somewhat more precise at this stage with the same data set. And again, this is all consistent with the run 1 measurements. One important result which has just come out from CMS is the first single experiment observation of Higgs decays to tau-tau. This is critical for establishing the direct evidence for the Yukawa couplings to fermions. This was observed with 5.5 sigma significance in the combined ROM1 Atlas plus CMS measurement, but with ROM1 data alone, it was not possible to observe this in a single experiment. So the latest CMS analysis of 2016 data obtains 4.9 sigma from 2016, and then in combination with ROM1 data, they get 5.9 sigma observed, 5.9 sigma expected. So this is a clear observation of this decay mode. These are actually very challenging measurements because observing the hadronic decay products of tau leptons in a hadron collider that's not an easy thing to do against the very significant backgrounds that we have. So this is a really, really important result. Moving on to Higgs decays to BB, this is a key mode for us, because as John mentioned, Higgs to BB dominates the Higgs decay, so the branching ratio is something like 58%. And we can obtain sensitivity to this by looking for the production of a Higgs boson in association with a standard model vector boson, a W or a Z, and then the Higgs decays to BB. Previously at Tevatron, there was a search carried out which had a significance for a possible Higgs at 125 GeV with a significance of 2.8 sigma, so not quite reaching the 3 sigma evidence level, although there was a maximum local significance 3.3 sigma at a different mass. The combined Atlas and CMS significance was 2.6 sigma. And so in the latest analysis from Atlas, this is actually, again, a very, very complex analysis. It requires many different channels to be combined. The selections are very sophisticated. They're not simple cut-based selections. They rely on very sophisticated multivariate techniques, boosted decision trees, to combine all the different observables to obtain the optimum separation between signal and background. So the primary analysis uses this boosted decision tree, BDT, but it's cross-checked by a cut-based selection using a more simple approach based around just the invariant mass of 2 B quarks. And this has been validated by, first of all, searching for the production of a standard model vector boson in association with a Z decaying to BB. So VZ, and indeed this was observed in the data set with a significance of 5.8 sigma observed, 5.3 sigma expected, in good agreement with the standard model signal strength expectation. So this convinces us that these techniques are working. We're not seeing significant biases in the analysis. So when we can move on and apply, effectively retune the boosted decision tree for the Higgs search, and then apply it to the data. And so in the run 2 data, we observe a significance of 3.5 sigma, with 3.0 sigma expected. And the cross-check with the cut-based analysis gives 3.5 sigma with somewhat lower expected significance. The combination with the run 1 data gives us 3.6 sigma observed, 4 sigma expected. So this is now evidence for Higgs to BB decays, which we've sought for a long time. And the observed signal strength is consistent with the standard model expectation. So mu of 1 is the standard model expectation. You can see from this data point here, this is sitting squarely on the expectation. And here's a nice W to E nu plus Higgs to BB candidate, where you can see here an electron here, missing transverse energy here, and then the 2 B jets from the Higgs decay. CMS have performed a similar analysis, and I won't go through the details again, but here again they check with a search for VZ, Z to BB production. They see 5 sigma significance observed, and then in the Higgs search they see 3.3 sigma observed from run 2 data alone, and then in combination with the run 1 analysis where CMS had a somewhat higher observed significance than Atlas, they obtained 3.8 sigma observed and 3.8 sigma expected. So again, the signal strength is in very good agreement with the standard model expectation, 1.2 plus 1.4. So I think from both experiments now we're seeing very clear evidence of the Higgs boson decays to BB. And so this bodes very well now for the coming analyses with the rest of the run 2 data at the end of the run, where hopefully we will now have, at that point we will have observation at 5 sigma of this process. Another key analysis is, in the Higgs sector, is the search for TTH production. This gives us direct access to the couplings between the Higgs and the top quark. As John mentioned, we can get indirect access from production in other channels, with decays to other channels, and also with Higgs to gamma-gamma, where we have loops which can incorporate top quarks and therefore give us access to the couplings. But here we actually are having direct access to the couplings. We can, of course, not get this from decays, Higgs to top, because that's kinematically inaccessible. So we have to rely on production. These are tremendously difficult analyses. I've probably, as I've been going through, the analyses have been getting more and more complex as I've been describing them. These are particularly difficult analyses because there are very, very major backgrounds from other standard model processes, for instance, TT-bar production with other standard model states, for instance, TT-bar BB bar, or TT-bar Z, or TT-bar W, and many other processes. Also, there are significant backgrounds coming from fake and non-prompt leptons, which have been produced or mistakenly reconstructed in the experiments, which can mimic the signatures for TTH production. And also, because the cross-section is rather low, we have to rely on combining many, many different channels. So in this CMS result, which was the first run-to analysis with the 2015 and 2016 data set produced, this is back in Morillard earlier this year, the CMS analysis observed 3.3 sigma in the multi-lepton final state. So these are channels where we have Higgs decays to, for instance, Z bosons or W bosons, producing leptons in the final state. 3.3 sigma observed, 2.5 sigma expected, using run-to data only. And so this was really a marker that we are now entering the regime where we can start to hope for evidence for this process from a single experiment. In run 1, from the combination of Atlas plus CMS, there was 4.4 sigma observed. In fact, the expectation was only 2.0 sigma, so there was some suspicion that maybe there was perhaps some systematics at play there, or that this wasn't sufficiently robust yet to claim clear evidence. So really the way to check this was to look at more data. But now, as you can see, we have some more consistent measurements between the observation and expectation. In CMS also, they have conducted an analysis looking for Higgs to tau in TTH production. It's less powerful than the multi-lepton channels, but it has potential to add significance in combination. And here, the observation was 1.4 sigma with 1.8 sigma expected. The signal strength, although this is not yet an evidence, the signal strength here also is consistent with standard model expectations. So then moving on to Atlas, here in Atlas we've taken two main approaches. We've looked for TTH production with Higgs to BB, and that's the first one. The second one is the multi-lepton channels, which CMS had, and I'll come on to those in a second. The Atlas BBT analysis actually only came out a few months ago with Higgs to BB, and we have 1.4 sigma observed, 1.6 sigma expected. So it's consistent with what we would expect to observe in terms of a significance, but nevertheless it's not sufficiently large to claim evidence for this process yet. However, Atlas at the same time has released its results from the multi-lepton channels, which, as I said, in the context of CMS, give us the greatest sensitivity to TTH production. And here, with run-2 data alone, with a very sophisticated multivariate analysis, we observe 4.1 sigma significance, 2.8 sigma expected. And then when combined also with the TTH Higgs to BB result, and also with some analysis categories from Higgs to gamma-gamma and Higgs to 4-lepton, which are also sensitive to TTH production. In global combination, we observe 4.2 sigma significance with 3.8 sigma expected. So that's clear evidence for TTH production at the LHC. And again, the signal strength is in good agreement with standard model expectations. This point here is sitting right on the line of 1. Okay, so I don't have a lot of time left, so I'm going to skip rather quickly through a few standard model measurements. There will be more on this in the talk this afternoon, so I won't say a lot about this. John has already shown this figure here, which shows the very large range of measurements which have been undertaken at Atlas in Run 1 and Run 2 of various standard model processes, and really demonstrating the excellent agreement between the measurements and the standard model predictions. And I'll just highlight a few of these briefly now. So one of the highlights of the Atlas Physics program in the past year or so has been the first measurement of the W boson mass at the LHC. This uses data actually from 2011, so 7 TeV data. This is a very difficult analysis, not because the signature is very challenging, but this is a very exceptionally high precision analysis. And so the control over systematics in the measurement has to be really unparalleled. And this does not come quickly, so it has taken 5 or more years to actually develop the understanding of the performance to get the required precision. One key question is modelling of some of the kinematic quantities which go into this measurement. So for instance, the lepton transverse momentum distribution, the missing transverse energy distribution. And one trick that we can use is that we can understand, for instance, how the W boson recoils when it's produced by looking at the much cleaner Z to LL events, which we can tag with an invariant mass requirement on the lepton pair. And that helps us to understand how Z or W bosons recoil when they're produced in this environment. So the end result is that we have similar precision to the best previous single experiment measurement from CDF, which you can see over here. So this is the new Atlas measurement here. And so we have a mass measurement of 80.37 GeV plus or minus about 19 MeV. The result is consistent with the standard model expectation. But in fact, to make further progress on this, which is something which we would really like to do with the very large data sets which we now have access to, really requires improved modelling, understanding in particular of this recoil of the W boson. So this is something which we are working very closely with our theorist friends on how to improve this understanding. Atlas has a recent measurement which has just come out on the top quark mass in 8 TeV Run 1 data. So this is something which we've been working on for a very long time to obtain with the most sensitive channel, which is a lepton plus jets final state. So this is where the TT bar, one of the tops decays to a W decaying to hadronic final state, and the other top gives a W which has a lepton and neutrino. So we have a new measurement of the mass here, and then the crucial ingredient here is that we then combine this with the measurements in the dilepton channel, where both tops decay leptonically. And in that combination, some of the systematics actually cancel out due to correlations. And so the end result is a significantly improved precision. And so we have 172.51 GeV plus or minus 0.27 plus or minus 0.42. And this is in good agreement with previous measurements from other experiments, also from CMS with a similar data set. So this is, again, boding very well for future measurements. Also in top quark physics, we have a few other recent significant results. One of them, actually, maybe I'll start with the second one, which is we have a measurement of the top pole mass, which we obtained by comparing the differential distributions of various kinematic variables for leptons from this 8 TeV Run 1 data set with the fixed order predictions in next leading order QCD from MCFM. And as you may know, some of you may know, one of the subtleties of top quark mass measurements now is that we're into a regime now where the quantities that we measure with the more traditional measurements like this one, it's not completely clear what it is that one is measuring here, because there are many other effects which can take place in this QCD effects which can take place in these measurements, which can cause this measured quantity to not be the same as the top pole mass. So this is an interesting measurement here, because here we are actually using leptons, which are not subject to so many corrections, hadronic corrections, and we are measuring a quantity which is perhaps a bit more directly comparable with pole mass that is used in theoretical calculations. So here we have a measurement of 173.2 plus or minus 1.6 GeV. The precision is not as great as that for what we call the Monte Carlo mass measurements that we see here, but nevertheless it's perhaps interpretable in a slightly more straightforward fashion. One other measurement which we've conducted as well is to search for production of a single top quark in association with the Z boson. The single top quark measurements have been a key focus of the top physics program at Atlas and CMS right from the beginning, and we previously have in fact obtained evidence for single top production in the S channel, in T channel, and also in associated production of top and a W, but never with a Z. And so we have this for the first time. The significance is 4.2 sigma observed, 5.4 sigma expected, and the cross-section is well in agreement with the standard model expectation. Okay, I'll just wrap up. Oh. I'm just going to finish off with a couple of slides on the future. John has shown a similar slide to this. John has shown a similar slide to this already. So this is a sort of long-term, medium-long-term plan for LHC running. We are currently here, and so the next big focus for the experiment development is preparation for the various upgrades of the LHC machine. First of all, for what's called the phase 1 upgrade.